we talk about AC, what we need to understand is how an alternating signal affects various circuit components like resistors, capacitors and inductors. So let's start our analysis with the most common component that we are familiar with, that is the resistor. So here we have a very simple circuit with a source and a load in the form of a resistor. And we have an AC source here. So this AC source is giving us an AC signal that is equal to Vm sine omega t. Now we know that according to Kirchhoff law, the sum of all the voltages inside a closed loop has to be 0. So whatever energy is being sent by the voltage source is being sunk into the resistor. So the potential provided by the AC source has to be equal to the potential that is being sunk across the resistor. So from that we get the relationship Vm sine omega t is equal to I times R, where IR according to Ohm's law is the potential drop across the resistor R. So from this relationship we can say that I is equal to Vm divided by R sine omega t. Now in this particular circuit, the Vm is the peak value of the voltage, the highest value the voltage will reach in any given cycle, and R is the resistance of the resistor. Since both of these quantities are not going to change, we can consider them to be constants. So we can say that we can define a quantity Im which is equal to Vm divided by R. So the earlier equation now becomes I is equal to Im sine omega t. Now the question arises, how can we calculate the amount of power that is being absorbed by this circuit or by this resistor? You may recall that the power for a system under DC conditions is given by the formula P is equal to V multiplied by I, where V is the voltage across the component and I is the current across the component. We can also define power in terms of the current and the resistance. We can also say that P is equal to I square multiplied by R. So these are two alternative ways by which we can define the power dissipated in a particular device, in this case a resistor. How do we modify this equation to account for the fact that we are dealing with an AC voltage and an AC current? To do that, let's substitute the values that we have just learned into this equation. So I is equal to Im sine omega t, and we know that power dissipated in the resistor is equal to I square R. So we can write this as Im sine omega t whole square multiplied by R equal to Im square times R times sine square omega t. So this gives us the expression for the instantaneous power that is absorbed by a resistor in an AC circuit. Now when we talk about the total charge transferred in an AC circuit, we run into a problem, because if you recall, in an AC circuit for the first half cycle charge is going one way, and for the second half cycle charge is going the opposite way. So at the end of any given cycle, at the end of any given time period, the total charge that has been transferred across the circuit is 0, because whatever charge is transferred to one side is returned to the other side during the next half cycle. So we can't really define an average value for the current for a cycle because it is 0. On the other hand, it is a different thing with power, because it does not matter what the direction of the current in the circuit is, power will be dissipated in the resistor, because it does not really depend on the direction of the current, but in fact on the magnitude of the square of the current. So by that definition we can come to the power dissipated on average across a cycle for AC power. Let's see. So here we have P given as Im squared times R sine square omega t. So we have average power, that is P bar, is equal to the average power over a given closed cycle, that is denoted by these square brackets, and this is equal to the average power dissipated across the resistor due to the current Im. Now once again, I square remains constant, the peak value of I square remains constant, the resistance remains constant, so we can take them out. We can define this as and the average of sine square omega t over a given half cycle, which is 0 to capital T. Now the question arises, how do we calculate the average value of this function sine square omega t for a given half cycle? To do that, what we do is, for any function that is defined for a time period 0 to t, the average value for that function is equal to 1 upon t integral 0 to t of this function. In this case, it is sine square omega t dt. So we can use an identity, a trigonometric identity, to make our work easier. Let's see how to do this. We know that sine square omega t is equal to 1 minus cos 2 omega t by 2. So out of this, we can say that if we are taking the average for a given cycle for this function, we are taking the average of 1 minus cos 2 omega t divided by 2. So we can write this as 0 to t 1 upon t 1 minus cos 2 omega t by 2 dt. So we can split this into two parts. We can write this as 1 upon t 0 to t dt by 2 minus 1 upon t cos 2 omega t by 2 0 to t dt. If you were to solve this integral, what you would find is, for any trigonometric function of the form cos omega t, the integral of it for one closed cycle is equal to 0, because over a given closed cycle, the entire integral reduces to 0. So the only term that we will have left here, so this term is what we are concerned with. This term will go to 0. So we can remove this, and solving this integral, we simply get 1 by 2 as the answer for this integral. So that means if we put this value into the original equation, we have P bar, that is the average power, is equal to the average of I times R, that is equal to Im R times 1 by 2, that will be I square m, and 1 by 2. So this comes out to be I square m R divided by 2. This gives us the average power for a resistive circuit. Now the question is, can we define a value of current which will dissipate the same amount of energy over a closed cycle which is equal to this amount? So we can actually do this. We can say that this quantity here is equal to some average value of I given by capital I squared times R. That will give us, since R is cancelled, we get the figure Im upon root 2, which is equal to 0.707 Im. And this figure, 0.707 Im, is the root mean square power for this circuit. and this is slightly less than the peak value of the current in the circuit.
Manorama Horizon. Learning made simple.